So we learned that uh, the temperature has an influence on reaction rate. So temperature increases for a given reaction, the rate of the reaction increases for most of the reactions. And based on Maxwell distribution and collision theory, Arrhenius explained why temperature, how rate of reaction increases and temperature increases. Uh, that when you increase the temperature, activation, the threshold energy, number of molecules that attain threshold energy increases. And also we defined energy of activation. Energy of activation is actually difference between the threshold energy and the actual energy the molecule possesses. That for a given molecule, uh, the energy of activation EA, energy of activation EA, and that EA amount of energy should be given to the molecule to activate it, just to attain threshold energy. So molecule with the threshold energy will collide with each other and convert it into product. This is what I explained in my last video. Now let me explain this Arrhenius equation. Arrhenius, the observation is when you increase the temperature, the rate actually increases. This is experimental observation. You'll note that rate constant actually increases with the temperature. You can write rate of reaction increases, as we know, when you increase a concentration, right? But we are not changing the concentration, but we are changing the temperature. So here I'll write T. K is a function of T. Rate constant increases by increasing the temperature, but the concentration is constant. You are not changing the concentration to carry out this reaction. What happens is when you increase the temperature, rate constant increases. So rate and rate constant, they are one and the same when you keep the concentration same to carry out this experiment. So based on the experimental observation, Arrhenius actually gave an empirical formula. He just noticed the experimental observation and he found that K, its rate constant, is a function of temperature, right, is exponentially related. He actually analyzes the experimental data, and he found that K is exponentially related with temperature. So temperature increases, K is actually increases. This relationship is exponential relationship. And looking at the experimental observation, he has given an empirical formula that it is not theoretically derived. It is based on the experimental. He has given this equation. E power minus EA. EA is activation energy by RT. EA. So this is Arrhenius equation. So if you look at the relationship K and the temperature, they are exponentially related. This is Arrhenius equation. Now you just take a logarithm. Here the terminology A is called A, here it is called a pre-exponential factor. Pre-exponential factor, because this is exponential, so this is pre-exponential factor. A is free exponential factor, or this is also called frequency factor. Frequency factor. A is sometimes, for some reactions, A depends on temperature, but here we assume that A is constant. It is independent of temperature. But there are some reactions, it seems, that depends on A value depends on temperature. So just to recall, rate of reaction increases when temperature is increased. Arrhenius observed based on the experiment that K actually exponentially related with temperature. So based on the experimental observation, he has given this relationship is called the Arrhenius equation. In the Arrhenius equation, A is pre-exponential factor, and this is also known as frequency factor. Frequency factor, why is it? The unit here, the unit of this exponential, no units for when you take exponential, unit will not be there, so no unit for this term. So unit of A will be equal to unit of K. If you consider it is a first order reaction, the K is actually second inverse. Unit of K is second inverse for a first order reaction. So the unit of A will be second inverse, right? So since since this is exponential term, this has no unit, and so that therefore this has no unit, then the unit for A will be equal to unit for K. So this K, unit for K is second inverse, therefore A will be, the unit of A will be second inverse. So second inverse is actually unit for frequency, right? Frequency, cycle per second, right? So second inverse is the unit of frequency. That is why A is said to be frequency factor. So either you call it as free exponential factor or frequency factor. Now I'm going to take a logarithm. Just take logarithm. This is log A minus EA by RT. And this is a straight line equation, right? Minus EA by RT. Or let me separate it, 1 by T plus logarithm A. This is Y, this is M, X plus C. So if you plot, if you plot 1 by T in the x-axis and logarithm K in the y-axis, I'll get a straight line with a negative slope. See, M slope is actually negative, so I'll get a straight line with the negative slope. And if you take a slope of this straight line, I will get slope equal to, this is slope, right? EA by R. EA by R equal to dy by dx. So from this, taking the slope of the straight line, I will get, I can find out energy of activation for a reaction. And the intercept C equal to logarithm A, right? So just extrapolate it to y-axis and find out the intercept. This is equal to logarithm A, pre-exponential factor. So at various temperature, find out rate constant and plot logarithm K in the y-axis and 1 by temperature, 1 by T in the x-axis, and take a slope. From the slope you can find out energy of activation. From the intercept you can find out pre-exponential factor or frequency factor. Now just I'm going to differentiate this equation. I'm going to differentiate this equation. Logarithm K equal to logarithm A minus EA by RT. I said this pre-exponential factor is actually constant. I'm going to differentiate d logarithm K. This is 0. minus EA by R. I'm going to differentiate d T inverse. If I differentiate, I'll get d, in differentiation of x power n equal to n x power n minus 1 dx. So therefore this is, I've written, okay, minus 1 t minus 1 and minus 1 and dt. So minus into minus will become plus, and EA by R T inverse 2 dt. Therefore d logarithm k equal to EA by R T square dt. Now I'm going to integrate this equation with the limits. That is, let me say, at temperature T1 the rate constant is K1, at temperature T2 rate constant is K2. So with this limit I'm going to integrate this equation. Temperature T1 to T2, d logarithm k equal to EA by R. Both of them are constant. Energy of activation is constant for a given reaction at a given temperature. Is 1 by T square dt. This is K1, right? K1, this is K2. This is limit because this is K. Here temperature T1 and T2. Just integrate. This is logarithm K, K1 and K2. This is EA by R. We just integrate, say, integration of 1 by T square dt equal to, I'll write T inverse 2 dt. Integration of x power n dx equal to x power n minus 1 by n minus 1. Okay, this is therefore t power minus 2, sorry, this is plus 1, it's not minus 1. So t power minus 2 plus 1 divided by minus 2 plus 1. That's all. So this is t my inverse 1 by minus 1. So this is the integration. Let me write this, or this can be written minus 1 by t. Minus 1 by t. The limits are t1 and t2. Now apply the limits. Logarithm k2 minus logarithm k1 EA by R minus 1 by t2 minus of 1 by t1. This is log A minus log B, log A by B, EA by R. This is minus into minus plus, so 1 by t1 minus 1 by t2. EA by R, I can write, just take LCM, I can write, and when you, this is natural logarithm, you can convert it into base 10, logarithm base 10. So logarithm k2 by k1, 2.303 must be multiplied, then this 2.303 is taken this side of the equation, right side of the equation, so I'll get T2 minus T1 and T2. So at two different temperature, T1 and T2, if you know rate constant value K1 and K2, you can find out KEA. Or if you know EA value, if you know at temperature T1, if you know at temperature T1 the corresponding rate constant value K1, then for any other temperature, let me say T2, you can find out K2 value. So this equation is another form of Arrhenius equation. This is a more important form of equation. This is used to solve many problems, right? So I just explained the effect of temperature. Arrhenius has given an empirical formula, and it relates actually the rate constant with the temperature. We found that it is exponentially related, and Arrhenius said that it is exponentially related based on an experiment. That is also true, because for many reactions, if you most of the chemical reactions, if you plot rate versus temperature, rate versus temperature, if you plot temperature, you will get a curve, exponential curve. It's not, this is exponential curve. This is true for majority, most of the reactions, and this is true. Okay, that's all.